What's up, grade 12s? I hope you guys are keeping warm. Let's have a look at the homework that I gave you to do. We did pay exercise 7 on page 111. So let's just quickly run through the answers, how I expect you to answer this in the exam. This tends to be a question quite often in the exam, so we'll just get through how I want you to reason it out. I'm going to do a couple. And then for those of you that might have struggled, it might help you to stop the video and retry the rest. But you'll see with exercise 7, they're asking us to sketch the following graphs on each of the following functions, showing all intercepts with the axis, stationary points, and the point of inflection. Afrikaans students, I'll repeat everything in Afrikaans afterwards. So for question A, so Afrikaans students, if you want to skip ahead to the Afrikaans, where I start speaking Afrikaans, you're more than welcome to do that. For question A, B, C, D, E, F, G, and H, we're going to do the exact same thing. We're going to need our function f. We're going to be using this equation. We're going to need the derivative, which is 3x to the power of 2 minus 6x. Remember, we take the exponent, we multiply it with the coefficient in front here, and we subtract 1 there. So 3 times 1 is 3, and then we subtract the 1 there, we get the 2. Over here, 2 times negative 3 is negative 6. We subtract 1 there, and we get x to the power of 1. And then we also need this. So as soon as you get this question, you can already start just by doing that. It's going to make life much easier for you. And then we solve this like we do every other function. So we say, for this one, we need to get the y-intercept. Remember, we want to draw the original graph. So we want to get the y-intercept. And we do that by subbing x equal to 0. Now you'll see if you do that, if you take this function and you make x equal to 0, you're going to get 0 to the power of 3 minus 3 multiplied with 0. And you'll get 0. So we get the y-intercept will be 0 and 0. Now you'll remember in class I said we could already see that this y-intercept would be 0 because there's no constant. If there's no constant, it would be 0. Like if we look at all of these other functions, let's look at c for instance, there's no constant. So that y-intercept would also be 0. Over here, there's a constant of negative 2. So this y-intercept would be negative 2. Over here, this constant is plus 14. So this y-intercept would be 14. Because we know that when we substitute x equal to 0, all the x's will fall away, and we'll just be left with a constant. All the x's fall away, we'll just be left with a constant. All of the x's fall away, we'll just be left with a constant. Okay, so that's just a quick way of looking at what your y-intercept would be. I expect you in matric to be able to do that. Now, this would be the part that's a little bit new to us. So we'll spend some time talking about the x-intercept. Now, we can mostly use our calculator to solve this. Right? We're using our table method on our calculator to solve this. So that would be the quickest way to do this. But in this case, it's quite easy to see what the x-intercepts would be. If we take out our common factor of x to the power of 2, we'll have x minus 3 left there. Now, if you look at the y-intercept, you'll notice the x value is 0, which we want with the y-intercept, and then we get the y value of 0. Now, to get the x-intercept, we make y 0. So we see that our x-intercept is also going to be 0 and 0. It's turning on the origin. But let's have a look at how this would work. For our x-intercept, what do? We sub y equal to 0. Or in this case, y is represented by f of x. So we sub f of x equal to 0. Okay, so we get 0 is equal to x to the power of 2, x minus 3. This is our zero product rule from grade 9. We learned this in grade 9 that if you've got one term on the one side, it's consisting of a couple of factors. If you've got one term on the one side, if this is equal to 0, that whole equation would be true. The whole thing would be equal to 0. This would mean x is equal to 0 or x is equal to 0. Remember, it's x to the power of 2, so it's got two solutions for x. It's turning out of x twice. Or it's where x minus 3 is equal to 0. So where x is equal to 3. So far we've got the y-intercept, 0 and 0. We've got x-intercepts, 0 and 0. and 3 and 0. Now remember, this one is repeating twice because it's x to the power of 2. Okay, so we're going to have 2 of these x-intercepts. And I'll explain what that means just now. Next up, we want to calculate the stationary points. And the stationary points are given by this over here, our first derivative. To get our stationary points, we always sub the derivative equal to 0. That will give us our stationary points. Our stationary points, we make derivative equal to 0. We get 0 is equal to 3x to the power of 2 minus 6x. I would divide straight through with 3 in this case. Some of you prefer to take out 3 as a common factor along with x. I've got no issue with that. It doesn't matter. And we are left with x minus 2. What I've got a big issue with is if some of you want to divide with x. We're not allowed to divide with x. We can never divide with a variable. We don't know what the value of the variable will be. Now, in this case, we've got our zero product rule again. You'll see one term on this side with a couple of factors. So that would mean this. This is equal to 0. That would make the equation true. Or if this is equal to 0, that would make the equation true. So there we've got x and 0 and x is equal to 2. Now, remember, these are stationary points. Just because I've made the derivative equal to 0 doesn't mean the y value for these x values will be 0. It can be, but that's not, we're not sure about that. So what are we going to do? We're going to take these x values and we'll sub them back into the original equation because this is the function that we're drawing. So we want to know what the y values would be. Now, looking at our previous work, we should already know that when we make x equal to 0, we should be getting 0. We can see it over there. We can see we did it over here. And yeah, we also got one of them over here. So when x is equal to 0 or y is equal to 0, so one of our stationary points, also known as a turning point, because our gradient is 0 at the turning point. And remember, if there's one thing that we know that our derivative is a gradient. So what we're calculating when we're making our derivative equal to 0 is we are calculating where does the function f have a gradient of 0. So if I want to calculate what the x values are when the gradient is 2, we'll make the derivative equal to 2. Okay, and then over here we'll do the same thing with x equal to 2. We'll sub x equal to 2 into the original equation, which is f. That's 2 to the power of 3, which is 8, minus 3 times 4, which is minus 12. So 8 minus 12 is minus 4. So this one would be 2 and negative 4. So there we've got some stationary points for our function, which is interesting. And this sometimes it stumps you guys in the exams because now we've got 1, 2, 3 points that are identical. So how do we bring that into play? I'm going to explain that now. The last thing that they ask us for is for the point of inflection. So the point of inflection we get by letting second derivative equal 0. So we've got 0 is equal to 6x minus 6. And if you solve that, you'll get x is equal to 1. Now again, you guys, we are drawing f. Okay, so we want to calculate x and y on the original function. You don't want to sub this back in here or back in here. It's not going to make any sense. All right, so we sub this back into the original equation and we calculate that when x is equal to 1 on the function f, we get 1 minus 3 times 1, which will give us negative 2. So our point of inflection is 1 and negative 2. Right, and now we can finally sketch this. So just looking at what we've got the y-intercept, which is 0 and 0. We've got the x-intercept, which will be 0 and 0, or 3 and 0. We've got the stationary points, turning points of the cubic function, which we see are 0 and 0, 2 and negative 4. And then we've got the point of inflection. Please make sure you understand this is point of inflection. I'm using at this stage, we also use point of intersection, the same notation there, but this is point of inflection. And we got that this was 1 and minus 2. So the last thing that we need the original equation for is we need it to determine how the shape of the function looks. So there we've got that x, everything that we need to draw it. And we're only looking at the a value. Remember with our quadratic function, if the a value is positive, it's a smiley. Now this, with our cubic function, if the a value is positive, it's a smiley at the end. So the final part of the graph, because this a value is equal to 1, equal to plus 1, that's a positive value. That means the last part of the cubic function is a smiley, which means the first part has to be a frowny. Okay, that's one way of looking at it. The other way of looking at it is it starts increasing, it ends increasing. I always remember that the last one goes up and then you'll automatically, if you draw it correctly, it falls in. But a value is a plus, so that's a smiley. So the last part should be smiling. That part should be look like that. So this is how we think the general shape is going to be. And now we will draw it. I don't see a lot of negative values over here. So I'm mostly going to be drawing on the positive x-axis, something like this. This drawing will not be to scale. We plot our points. There's the 1 point, 0, and 0. Then x-intercept 0 and 0. Okay, cool. There we go again. And then at 3 and 0, so 1, 2, 3. Let's count in twos. 2, 4, 6. So there's 3 and 0. Then stationary points. So these are the points where the graph is turning. You'll see here, remember, where these are turning points there and there. So it's turning at 0 and 0. Okay, so I expect it to be turning there. I don't know if it's going to look like this or it's going to look like this. But I remember, wait, it's supposed to be a frowny first. So if this is a turning point and this is the first turning point that I've got, this should be going this way. But let's just double check. That's a 1 stationary point. Then the other one is at 2 and 4. This is 1, 2, -4. So let's keep this one normal. -1, -2, -3, -4. There we go. Okay, so according to this, the turning points will be at 0 and 0 and 2 and -4. This one is more to the right. And we know that part should be a smiley, so our turning point should look something like this. That means this would be our first turning point. That turning point should look something like this, because they have to meet each other in the middle. And now we've got a point of inflection we can draw. So there's 1 and -2. That's over there. Okay, so let's draw this function. It should look something like this, going in here, turning, going over there, turning, eyeball, going through the point of inflection, turning again, finally exiting through the x-axis over there at point 3. So there we've got 0, 3, 1 and -2, 2 and -4, and that's how that function looks at this stage. Okay, so for the next couple, I'm just going to do it a bit quicker, but you get the general gist of it. I'll spend some time with the x-intercepts because that's something new, but we did look at the x-intercepts for B as well as G and F. So for B, I'm not going to spend too much time on that. We'll just be looking at what we need to draw it. So it's minus x to the power of 3 plus 6x to the power of 2 minus 9x. So to draw this function, we'll do the exact same thing we did with question A. We need G, our original function. We need G prime, first derivative. And we also need our second derivative, which is this. Okay. We see our y-intercept should be 0 and 0. Our x-intercepts, we'll be using our calculator for. Now remember, when you're calculating your x-intercepts, in this case, we can solve it like we normally would. So we've got 0 over there. I would divide straight through with a negative because we've got 0 on this side to get rid of the negative. So we've got x to the power of 3 minus 6x to the power of 2 plus with 9x. We take this out as a common factor. And we factorize. So we get that the x-intercepts would be x equal to 0, x equal to positive 3, or x equal to positive 3. So x is equal to 0, or x is equal to positive 3, or x is equal to positive 3. So these coordinates would be 0 and 0, 3 and 0, 3, 0. Now remember what is important about this. If your x-intercept is repeating, if it's the exact same value twice, then that means our function is turning on that value. So what I'm thinking of now is when I'm getting the stationary points, I'm thinking that one of the stationary points should be x equal to 3. Okay, but let's see if that holds any water. So let's get our stationary points. I'll just use the shorthand SP for this one, and we'll make our derivative equal to 0. Let g prime equal 0. And we'll divide straight through with the minus 3. And we'll get x squared minus 4x plus 3. Factorize. And we'll get the following. So x will be equal to 3, or x is equal to minus 1. Now, please remember we are drawing the original function g. So we don't want to know what these coordinates are on the derivative. We want to know what these coordinates would be on the original. So we take those values and we sub them in to the original. Now, I would already tell you, without doing any calculations, that this value should have a y value of 0. Because I saw it over here. When my x value is equal to 3 on the original graph, my y value is equal to 0. This 0 has nothing to do with this 0 over here. So the coordinates for that point would be 3 and 0. Right, let's check for this one. We sub in 1 into the original equation. That's minus 1. Plus with 6, that's 5. Minus 9, that's going to be minus 4. So when I substitute 1 into the original equation over there, minus 1 plus 6, which is 5, minus 9 times 1, which is 5 minus 9, which will give you negative 4. So we get 1 and minus 4 would be the stationary point over there. Okay, next up, we need the point of inflection. So let's get that going. Point of inflection. This is shorthand I'll use there, which means we're going to take our second derivative and make it equal to 0. We'll solve that and we'll get that's where x is equal to 2. We're drawing the original equation, so we take this, we sub x equal to 2 back into the original equation, and then we get minus 8 plus with 24, minus 8 plus with 24 minus 18, which is negative 2. So this point over here should be 2 and minus 2. Okay, so let's have a look at what's going on here. We've got the y-intercept. We've got all of these x-intercepts. We've got the stationary points. And we've got the point of inflection. So now we need to look at the original equation, which is this g of x here. We look at the a value. The a value is negative. That's minus x3, 6x2. What was it? 9x. It's a negative 9x. Okay. So what we see over here is we see that the a value, the value that's attached to x cubed, is equal to negative 1. Because it's negative, we know it's going to be a frowny at the end. So it's going to look something like this at the end, which means the initial part should be smiley. Okay, but let's see if what the values that we've calculated, if this is true for this one. So I don't see a lot of negative x values. Most of them are positive. So again, I'm going to be drawing mostly on the positive side of this. The y values don't tend to stretch out too much. They're going down to -4. So let's just give a couple of negative values over there. And let's plot these points. Y-intercept first point, 0 and 0. Next up, it's turning, well, x-intercept 0 and 0, 3 and 3. So 1, 2, 3. Let's count in twos, otherwise it's going to be quite squished. 1, 2, 3. Over there, that will be another one. And then let's look at stationary points. Oh, stationary points. So it's turning over there as well. I need to be careful. I need to remember that. And then it's turning at 1 and -4. So let's see, that's 1 and then 1, 2, 3, 4. So it's turning over there. According to this one, so this is my stationary point. This is my first stationary point, and this is my second stationary point. The first stationary point, it should be smiley. So it should be going something like this over there. And then the second stationary point, which is 3 and 0, if I'm going from left to right, is a frowny because my a value is negative. So it should look something like that. And then we've got a point of inflection at 2 and -2. So that's 1, 1, 2, and then, so there, point of inflection. Okay, so it looks like it's going to work out. We've got turning over here, so it should go down, turn there, go through the point of inflection, turn there again, and go down further. So this would be G. And this is 3. This is 0. This is 1 and -4. And this is the point of inflection, 2 and -2. So those are the first two functions for the homework that I gave you to do. I'm going to upload this along so those of you that need to practice can practice some more, and then I'll finish the rest of the homework for you. But yeah, please make sure that you're following along, that you understand what's going on there. I'll be uploading the next one shortly.